Okay, so we've already looked at this thing called the linear case. So say basically if we had two derivatives, okay, so dx by dt and dy by dt, and both of those things were equal to linear functions. Okay, I'm over this right hand side now. So both of these things were equal to linear functions. Well, basically what we could do, we saw with the linear case, what we could do is take these two functions and combine them into one equation. Okay, so we had dx by dt is equal to some coefficient matrix, which corresponds to the a, b, c, and d, a, times x, which corresponds to our x vector, which remember is different to just our ordinary x, it's an x vector now, and that corresponds to the variables which we've got, x and y, and then plus some constant vector, constant matrix, which corresponds to the constants which kind of tag along at the end here, so k1 and k2. And then what we could do is, via a very clever change of coordinates, so basically if we set this equal to 0, then we would get a critical point, an equilibrium point, so the point where a maximum or minimum occurs of these two functions. Okay, if we set this thing equal to 0, this dx by dt is equal to 0, then we get an equilibrium point. Well, this equilibrium point could lie anywhere in the plane. Okay, so what we want it to do is lie at the origin, because that makes things so much easier, because we just end up with zeros, which just we don't have to worry about numbers. All right, so we can move our equilibrium point to 0, 0 by making this transformation here, x tilde is equal to x minus x equilibrium point. And so basically this equation here, this dx by dt, basically turns into dx tilde by dt equals ax tilde. And that was the linear case. Now we want to do something very, very similar with what's known as the nonlinear case. So the linear case is where the right-hand side of these two functions here, x dot and y dot, were just linear functions. Okay. Now what we want to consider with the nonlinear case is when the right-hand side isn't a linear function. So in other words, it's going to be some function of x and y and another function of x and y. Okay. Now, again, we can combine these two things into one function quite nicely. So we've got dx by dt, all right, and that's going to be equal to, now we've got to be a little bit more careful, because we've got now these two functions here. So we're going to end up with a big function, okay, or a matrix that corresponds to these two functions in here. Okay, so f and g, and then we're going to have a if you like, how am I going to put this? A constant vector which comes along for the ride, okay? And that constant vector is a bit like this k over here, okay? So suddenly now, or this a here, it's basically just the coefficients, if you like. Don't worry too much about that constant vector, why it's there. You just have to know that it has to be there in order for the maths to work out. Okay, so we can write now our function like this, and again we can do a similar kind of change of variables, change of coordinates, and we can turn this into dx tilde. It's exactly the same change of coordinates. So we can find the equilibrium point of this function now. Say we can find the equilibrium point of this function, and then we can move that equilibrium point to 0 by doing this change. This transformation, x tilde, and then we end up with dx tilde is going to be equal to f of, what we're going to end up with, yeah, that's going to get a bit messy actually. We are going to get that, we're going to get dx by t tilde, actually I'm just going to leave it as dx by d tilde, I think, d tilde, but not worry about the right hand side, because the right hand side is, believe it or not, is actually clearer if we consider the multivariable case. Just see if I can make this work. Okay, if we consider the general case, that kind of makes things a little bit clearer. Okay, so this is basically what we're trying to do. Now, I've just looked at two variable case. So in other words, we've got x dot and y dot, but in general we can have as many variables as we like. We can have as many derivatives as we like. So say for example we have n derivatives, so n variables, so therefore n derivatives. This is being ridiculously slow. Let me see if I can close it down and start again. Okay, so now instead of just considering the case where we have two functions, f and g, or dx by dt and dy by dt, let's consider the case where we have as many functions as we like, so n different functions. Okay, so the multivariable case, we call that. Now, if we have the multivariable case, then what have we got? Well, we've now got n variables, right? So we write our x, like we would write over here with our linear case, our x would be x and y, okay? We can now write our x is just all our variables put together. So we have x1, x2, x3, x4, right the way through to xn, okay? And like we would write our A as our coefficient matrix, so our if you like, our coefficient matrix is just the operator of how am I going to put this? The A is just the operator matrix of our variables, isn't it? Because if we multiply this A by x, then we'll get ax plus by. Okay. Well, if you like, our operator matrix now is just going to be our functions, the things which we're going to have to multiply by our variables. Okay, so we're going to have our operator matrix is just going to basically be all our functions put together. So our operator matrix, let's call it F, is going to be given as F is equal to all of our functions. So F1, okay, right the way through to Fn, okay. But our functions are going to be of all our variables, aren't they? Of all our x. So we're going to have right the way through to xn, okay. And the same thing here, and this is going to be of all our functions. Okay, all our functions are going to be of all our variables. Okay, like I say, it's not the prettiest case in the world, but it's a simple enough idea. Okay, and then also we can derive the equilibrium points. Okay, by setting all of our our dx by dt when we get it. When we set it equal to 0, then we can get our equilibrium points out. And our equilibrium points, well, how many equilibriums are going to be? Well, one for each dimension, and there are n dimensions, therefore there's going to be n equilibrium points. So xe1 right the way through to xen. Okay, so we've got n different equilibrium not n different equilibrium points, that's 1 point, okay, but that's 1 point in different dimensions. So for example, if it was in 3 dimensions, xe would be xyz. Okay, that's all I'm basically saying there. Okay, it's not playing, is it? Sorry, my pen's not rubbing out. There we go. Okay, I'm just going to make this a little bit smaller now so we can have a little bit more room to work. And then basically what we're going to do is we're going to represent that as one kind of what we want to do now is represent, like we did up here with our linear case, we want to take these functions and represent it as one, or these two equations and represent it as one equation. We're going to do exactly the same case with our n multivariable case. We saw it happen with the 2 variable case. Let's happen with the multivariable case. So we've got dx by dt, okay, where x is just going to be all our variables, differentiated with respect to t. Well, that's going to be our function, and then we're going to have all our variables in there, which I'm going to represent by x. Okay, so this is our operator, if you like, f, and that's going to contain all our functions of x, which is all of our variables, and then we're also going to have a like we say, a constant vector which comes along, if you like, for the ride. Okay, so this is what we're going to end up with. Well, we've got our equilibrium points. Now we can move those equilibrium points, because if you like, there's going to be n dimensions. Okay, now, so I'm just going to consider 3 dimensions. Let's say it's over here somewhere. Well, we can move that down to there just by moving in the x direction, moving in the z direction, and moving in the y direction as appropriate. So basically till we get it into 0, 0. So it's exactly the same transformation as we had before. So x tilde is equal to x minus xe. Okay, and if we do that transformation, then we get this. So we get dx tilde by dt is going to be equal to f. That's going to remain the same. It's just all our functions. Okay, but now our variables are going to change, aren't they? Because we've moved our variables. Because, well, look, if I just rearrange this, I can replace x for what? Xe plus x tilde. Are you happy with that? I've just done a little bit of algebra. Moved from that side. I've moved that xe over to the left hand side, so I just get that. So I can now just replace x just with xe plus x tilde. Okay, and I've still got my integration. Sorry, not my integration, my constant vector which comes along for the ride. Okay, so hopefully that makes a bit of sense now, how I've got kind of from there to there. It's exactly the same case as the nonlinear case. I've just made a substitution for x. Okay. So now I've gone from there to there. Okay. So now what do we want to do? Well, we want to try and expand this out. Okay, and we can expand this out. We want to try and do something with it. So let's try and expand it out. And we're going to expand it out using this little nice little thing which we've learnt before called, that's not working at all, is it? Sorry, my computer is really, really slow. I suspect it's about to overheat in a minute. Right, whatever. That's just staying there now then. What we can use is we can use this thing called Taylor's theorem. Now, do you remember Taylor's theorem? I'm going to use the one-dimensional case because the sort of I'm going to use the one-dimensional case to explain it, and then obviously I'm going to have to use the nth dimensional case to expand it and everything. But I'm going to use the one-dimensional case to explain it just because it looks nicer and looks a little bit simpler. So, in general, if we have a function, okay, well, we can express that function or approximate that function using its derivatives. So let's say it's an analytic function, so we can differentiate it. Okay, and we can differentiate it as n times as many times we need. Okay, and that's going to be represented as the function evaluated at 0. Okay, plus the function differentiated. The function differentiated and then put 0. Okay, times x, and then we're going to have all these higher order terms. Okay, so it's going to be f double dash of 0, x squared over 2 factorial plus f triple dash of 0, x cubed over 3 factorial, etc, etc, etc. Well, I'm just going to represent all of those higher order terms, okay, in there, just by something, okay, and I'm just going to call it phi of x, okay. So basically all that's saying is that all the higher order terms, I'm just going to call it phi of x. So essentially I can just write it as f of 0 plus f dash of 0 times x plus this thing, which is the higher order terms, okay. So what does that actually mean? Well, I'm trying to approximate my function as best as I possibly can. And remember that this is my function. Say if this is my function, and just draw it out. Okay, so it goes all over the place. Something like that. When it catches up with me. Come on. Yeah, it's being so slow. Really sorry. So this is my function. And basically what's going to happen is that as I consider more and more terms, I'm going to have a better and better approximation. Okay, and so in other words, I'm having a better approximation over a wider interval. So I start at 0, okay, and I approximate it. So I just evaluate my function at 0. Well, obviously I'm going to get the function at 0 then, aren't we? I'm going to get an exact value for the function at 0. But then I'm going to add to that the derivative of the function at 0 times by x. Now, the derivative of the function, so I start off with just with a straight line. That's just my function evaluated at 0. Then I'm going to consider the... that's my function evaluated at 0. So I'm just going to start off... Let me try and draw this again. I'm going to start off with my function evaluated at 0. So I'm just going to have a point. So that's basically my approximation. It's just going to be a single point. Okay? And that's what my first term corresponds to. But then as I add more terms, so I add the next term, then that's going to be a line. Well, a line is obviously a better approximation of this function than just a single point. Okay? And then as I add another term, so my next term will be a power 2, so it'll be a quadratic, so it would look like that. Well, that's a curve, so that's a better approximation now. Okay? And then I consider a cubic. Well, a cubic is even more curvy than a quadratic, so that's an even better approximation now. So basically, with each term, I'm getting a better and better approximation of my function. Okay, I start off with a point, then I start off with a straight line, then I start off with a curve, then I start off with more of a curve, and I keep going, keep going, keep going. But if you notice that as I go, that's not a very well drawn parabola, there we go, that's a bit better, that as I consider values close to the equilibrium point, okay, well, as I consider more points, effectively what I'm doing is I'm moving away from this equilibrium point. I'm getting a better approximation for my function away from my equilibrium point. Okay, so basically, if I just consider my function or my approximation for my function close to my equilibrium point, okay, I only actually need a couple of terms. I only actually need those two terms, because that higher order term is just going to go to 0. I'm not going to need the higher order terms because I only want the value at the equilibrium point, which remember I've moved to 0, 0. So therefore I don't need that higher order term there. Okay, and of course my function evaluated at 0, and it's going to be 0 anyway, isn't it? Because it's going to go through the origin. Okay, so effectively what I've done is I've managed to reduce using Taylor approximation. This is just for one order, by the way. But I'm going to use this idea for my multi-dimensional case, or one variable. So I'm going to So effectively, I can just reduce it down to this. So my function close to equilibrium, so close to xe, okay, is just going to be approximated like this. Okay. So now my question to you is: we've got this. Okay, we've got this as my. I can just make that a little bit smaller. I don't know whether it will work. This is my Taylor's theorem. Just let that sink in for a moment. Okay, but my question to you is: what's going to happen for the multi-dimensional case? So I've got to consider my Taylor's theorem for a multi-dimensional case. Okay, and then we're going to do exactly the same thing. Well, it's not really a question, so I'm going to tell you. But we're going to do exactly the same thing as we did for the one-dimensional case with the multi-dimensional case. Okay, so there's my Taylor's theorem there, looking a little neater. Don't know why I did that, but never mind. So now what I want to do is I want to approximate f of x. What have I got? X plus xe, x tilde plus xe, mu. All right. So I want to approximate that. I want to approximate this function. Well, notice that I've got two. Come on. I've got two variables in here effectively. This is one variable. This is one variable in here. This x tilde plus xe, that's one variable. This is another variable. Okay, so I want to approximate this, and of course this is equal to, come on, this is equal to dx tilde by dt. Okay, so I can now say, using Taylor's approximation, I'm not going to go through Taylor's approximation now, but if you're not sure, go away and have a look at it. My Taylor's approximation is going to be given by this, x tilde by dt. This is just going to be this. So yeah, I'm just approximating this function here, but I'm just writing this function as dx tilde by dt. Okay, so I've got. Okay, so I've got f. So I've got my function evaluated at my equilibrium point, which of course is just 0. F mu. Then I've got my derivatives. Now I'm going to write my derivatives as something called the Jacobian. Okay, so this is the Jacobian, J. Okay, and that's going to be of my equilibrium points of my two variables. Okay, and then I'm going to just have my higher order terms like we had before. Okay, so like my x squared, my x cubed, my x whatever. Okay, so I've got my equilibrium point, I've got my constant vector, and I've got my variables, tilde, x tilde. Okay, so what's going on here? Well, like before, my function evaluated at 0 is going to just be 0. It's at the equilibrium point, which is 0. Evaluated at the equilibrium point is going to be 0. And likewise, I'm not going to need the higher order terms because I'm considering it close to the equilibrium point. So at 0, I only need basically the first two expansions for this. Oh yeah, this I've forgotten here. This in here, there should be an x tilde. Okay, because that's multiplied by x. It's a bit like f dash of 0 multiplied by x. Okay, that's effectively what that term is in there. Okay. Now, my Jacobian, I'm going to come back to what my Jacobian actually means in a minute. But essentially, because this goes to 0 and this goes to 0, I've now got approximation of my function as Jacobian of xe mu, and this is times by x tilde. Okay, hopefully that makes a bit of sense. So basically, at the equilibrium point, this is what my function is looking at. Okay. Now, what does Jacobian mean? Okay, so what is it? What is actually a Jacobian? Well, in order to explain that, it's basically just, if you like, I think of it just like a box of all my derivatives, all the derivatives that I can possibly have. Okay, so all my first order derivatives, all my first order derivatives. Yeah, it's basically a box containing all my derivatives. Okay, so it's a box of all my first order derivatives. So that's one Jacobian. Then if I want the second order Jacobian, then that's my box of all my second order derivatives, all the derivatives that I can possibly have. So if, say, for example, if I just start off with my example again, so dxt and then dy by dt. Okay, and that was equal to a function of x and y. That's what we started with at the beginning. Okay. So this is I'm just considering again my two, the thing which I started at the beginning. Okay, what can my derivatives be? Well, I can differentiate this function with respect to, so I can differentiate this function with respect to x. Okay, it's going to be partial derivatives because I can only ever differentiate with respect to one variable at a time. Okay, so I can have my derivative of my function with respect to x, but I can also have the derivative of my function with respect to y. Okay, because it's a function of x and y. And likewise with this function, I can have the derivative of my function with respect to x, but I can also have the derivative of my function with respect to y. It's a g there. Okay, so basically all I'm just going to do is I'm just going to put this into one box, if you like. Okay, I'll pull out a cardboard box, put all my derivatives in that box, and that's the Jacobian. Okay, but of course, in the nth dimensional case, which I'm not going to go into now because there's loads of them, there's going to be n different derivatives. Okay, so df by dx1, df by dx2, df by dx whatever, right the way up to df by dxn, and then likewise with the dg. Okay, and then of course we're going to have different functions, so it's going to end up with an n by n different matrix, which is going to be quite tricky to work out. But basically my Jacobian is just my matrix of my derivatives. Okay, and then what I'm just going to talk about very, very quickly is this thing called a hyperbolic equilibrium point, because there's two different types of, for non-linear systems, okay, you can have either a hyperbolic or it's not hyperbolic, okay, but if it's hyperbolic, then it's quite nice, and the reason why is because a hyperbolic case is basically where the eigenvalues are not equal to 0, okay, so if the eigenvalues are not equal to 0, an equilibrium point is hyperbolic if none of the eigenvalues of the linearized coefficient matrix has 0 real parts. Remember, the linearized coefficient matrix, that was just f. Okay, that was just f. If it has 0 real part, then the eigenvalues will not be equal to 0, and so therefore we end up with, basically I'll go into it in a little bit more detail, but if it's hyperbolic, then we can just treat the non-linear case as the linear case, okay, at values close to the equilibrium point. So close to the equilibrium point, if the eigenvalues, and if it's hyperbolic, then the non-linear case can just be treated as the linear case. Okay, and we're going to go on to that in a little bit of detail. But if it's close to the equilibrium point, then it's really quite nice because we just have to consider this linear case, and hopefully, if that made a bit of sense, if linear case made a bit of sense, then the non-linear case will make a little bit of sense as well. If we can just turn a non-linear case into a linear case.